Okay, so it now seems that we have started the broadcast, Radek.
Okay.
Okay, that's great. So
Great.
I hope everything is. I hope everything is working. Can you see my screen?
I can
not
see.
yet.
Oh, not yet. I can see you, but not your screen.
Okay, so yeah, yes, indeed, and I'll try my best. So now it should be yes. So you can see yes our faces. The
Yeah, two handsome guys and
yes
pants. Yes,
really yeah.
can see your first slide. Yeah.
Yes, so it's gonna be wait for it to like 1 minute or two. Yeah, and so yeah, so you can see this, you can see that. Okay, so let's do our best. Well, we will switch cameras somewhere shortly after the beginning. And what else? Let's have fun. It's okay. So it's 2 p.m. So once again, let's give it one last minute as usual, because we know very well by experience that the most people come in the shortly right after the beginning. So we will wait one last minute and then we will start the webinar. We will. By the way, Radek has new photo here, right? New image, new face.
Yeah. Brand new photo.
Much better, right? It's better. This one is better than the last one. It's really good. Yes.
Yeah. So many filters were applied to look like that. Yeah.
Where are they somehow? You're joking, right? So
Yeah,
this
I'm
is new
joking.
Radek, and this is old me. Yeah, and actually, I will use this red, this laser pointer. Okay, I will use it. I like it.
Yeah, looks cool.
Yes, I will use this laser pointer. Yes. Okay, anyway, so it's 1 minute. Yes, we will start a webinar. So I hope this can disappear. The cameras faces just go away. So yes, and we will start the webinar. So let's do it. Actually, it's started, so we will cut it here, or let's see. Okay. So hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you what we have done in the recent period. Especially the webinar is going to be dedicated to simulation-driven optimization, especially dedicated to turbomachinery applications. So I hope you can see us, I hope you can hear us, I hope everything is working well, and let's see what we can do. So yeah, the webinar is being recorded, and the recording will be later made publicly available on our YouTube channel as usual. So be sure that you won't disclose anything you don't want to disclose, because there will be a Q&A session dedicated to your questions and our answers at the end in the last part. So feel free to ask your questions anytime during the webinar, and we will be happy to answer all your questions. The most relevant questions will be answered right away in the webinar. The specific questions and will be answered later via email, but you can be sure that all the questions will be answered. That's some organizational information. This is me, and I hope together with us is my colleague Radek Máca. So let's check it. Radek, hello.
Hello, Luboš, and hello to the audience. Hello. I'm here live.
That's great. So let's make it happen. Is there anything I should mention, or are we going for it?
I think we are ready to go. Yeah.
Okay. So let's
ready to continue.
Okay. So let's go ahead. Radek, I think we can switch the cameras off, and hopefully we will remember
again to the end, right?
Come back again. So I'm switching the camera now, and I hope you can see my presentation. So again, today's presentation is about the simulation-driven optimization for especially for turbomachinery applications. The principles are valid for all the applications, but as you know, our company has a long history of turbomachinery applications, and we will stay in this field for today's webinar. Okay, so let me start. There are a couple of upcoming webinars. We are constantly working on what we believe is very, I would say, fruitful and promising for you. So the next webinar will be in 2 weeks. It's a new acoustic benchmark. We developed our acoustic module a lot. There are new features, new sensitivity tests, and a lot of new capabilities, and we are even more confidential in the direction we are going with our acoustics module. So the webinar which will be dedicated to acoustic simulations will be in 2 weeks. And we would definitely like to see you there. So talk to see you there. And yeah, there will be other webinars. I will just quickly go through them. So they're scheduled throughout the year, so you can find the more detailed information on our website. So I'm not gonna specify them one by one, just quickly. And I'll start with necessary general information. So yeah, so I promise I'll be quick, but still I have to say a couple of these general information. So CFD Support is the company. It's located in Prague, Czech Republic, and for 15 years we are dealing with CFD, FEA, FSI, optimization, and acoustics simulations. We create software for it. We do consultancy business, and all of it. Basically, it's know-how transfer over to our clients, and that's our world. So definitely, you are here on the right place here if you want to follow some of CFD, FEA, FSI, optimization, and acoustic simulations. Today's webinar is dedicated to optimization. So it will be it's a specific field where typically a lot of simulations or more simulations are run, and the best results are or the best lessons are taken out of it. Okay, so our flagship product, the software, is called TCAE. So we develop it here, and we provide it to the users. So it's called TCAE. It's a comprehensive simulation environment, which is basically a tool, a CFD code, which allows all these kinds of simulations. And it consists of several software modules, and the modules can communicate with each other and provide to everyone a very flexible set of tools. And its benefit is definitely that every user can set the workflow which fits his skills, experience, and resources to deliver the results in very, I would say, high quality, and it's definitely very flexible. Software is unlimited. There are no limitations on a number of users, job scores, hardware installations. It's really beneficial that the users can scale their resources to the fullest, and there are a lot of there's a wide range of licensing options and of way of using this software. So it's very flexible also in these terms. It's focused on, as already mentioned, it's focused on turbomachinery applications and external aerodynamics. So it allows the software to be accurate, to be really useful, because it's not a software for everything. It's software really dedicated to specific fields where it can be very efficient. It's accurate, it's automated, and it's in these terms it's very modern software, because it's already created with the intention to give the best to the users in terms of these features. Okay, there are a lot of benchmarks which are based on real projects we did in the past with real customers. We marked the details, and we were allowed to use them as benchmarks. So there are a lot of benchmarks where we compare the simulation data with the real physical measurements. That's very important because all the users are very polite about the accuracy. There are a lot of tutorials available, and also we have very, I would say, good technical support, which is our I would say specific feature that we are focused on good technical support, and it's in the name of the company after all. So it's this. The software is can be used for remote computing very well. It can be used on laptop. It can be used on PC. It can be used on desktop. It can be used on cluster. It can be used on cloud. It can be used remotely from home or from the office in Windows or in Linux. It has unique client server options. It can be run locally but simulated on the server. So it's very modern, I would say, in this terms. It's based on open source. It's very important that we do not develop everything from scratch. We use all the, I would say, important features and important open source pieces available in the market. We have mastered the ability to process and integrate these open sources into our simulation environment. And we have spent more than 40 many years over the on top of open source projects. So this already is value itself, because it's a lot of effort has been spent to deliver this software. Currently, the version is 24.03. Recently, we have made even new. The latest version is version 2 of 24.03, and we will release it very soon, perhaps next week. And for the future, we are definitely, we have a couple of goals. So we will definitely focus on optimization, develop it further, and we believe it's the very promising feature for the future. We will also focus on acoustic simulations. The module TCAE will be developed further. It's being developed very quickly, and it's again very promising. Next in the next webinar, we will introduce the new benchmark, which is again very useful and opens the door for a lot of new simulations of fun acoustics. And lastly, we are developing the new simulation module, software module, which is called T-Base, which will help create a large databases of results and allow users to employ machine learning and create their own surrogate models. It's very promising, and we will introduce it a little bit later. Okay, so today's topic is the optimization. So I will say a little bit what I think it's important to say about the optimization in CAE. So optimization, we believe optimization is pretty much a paradigm shift, which is a really big change in the throughout the field. Because in the past we know what we have done, right? It was basically a trial and error method. We have created the simulation, ran the simulation, and looked at the results. And this was an iterative process. We changed something, one parameter, two parameters, looked at the results, and then we were hesitating what was the cost of the change, etc., etc. So it was relatively, I would say, painful process, right? Which was pretty manual, and we sometimes now I call it trial and error method. We tried something and saw what's good or not good, and then we decided for the next step. But the optimization can be done in a much smarter way. We can look. I mean, we can iterate automatically to the best possible. So we believe that the optimization is a big shift from the trial and error method to the search for the best possible, and it's a big difference. We're engineers, and we believe that the world consists of parameters. So it can be the physical world can be described by parameters. And the problem is that there are a lot of parameters, right? So any simulation has more than 200 parameters easily. And any industrial product, which is going to be optimized, has another hundreds of parameters typically. So we are facing a huge multi-dimensional problem, right? Which is, the problem is that the human mind can imagine only 2, 3, maybe 4 dimensions, right? And then it gets lost. It's not been created for that. So it definitely has to be a machine which navigates us through this multi-dimensional system or multi-dimensional problem of so many parameters, because the system is extremely complex, right? And it definitely has to be a machine who does the process for it. It's definitely possible. There are algorithms for it. Our human mind can't imagine it, but it's not that difficult to use them numerically. Another important point is that the optimization process has to be somehow automated. It cannot be done manually, because it's so complex. And this automation also avoids human error. So it's another benefit is that we avoid human errors, and from the experience we know there are a lot of them in the practice in the real world. Okay, so optimization is a big paradigm shift. We were convinced about it. Let's continue with a couple of lessons we have taken. Intuition doesn't work. In multidimensional problems, intuition doesn't work. You cannot make any product better with just several parameters by making it up in your mind, right? I have here a little example. These 4 axial fans, they look the same for the first sight. Of course, this is just the front view. We do not know any more details, but I have intentionally picked 4 similar fans, but the point is that their efficiency differs by 10%. So this fan looks similar to the other fans, but its efficiency is 36%. This fan's efficiency is 40%. This one's efficiency is 42%, and this fan's efficiency is 46.8%. So for the first sight, for us, they look the same way, but they are not the same. They produce different flow. Maybe you can notice little details, which altogether make the difference in the efficiency of 10%, which is huge, right? Because the 10% of energy will be either lost or gained. So it's really a big deal. So the point is, the intuition doesn't work. So we definitely have to use the machine or the algorithms to optimize. Optimization is not machine learning, right? We have in the recent period, we have heard a lot about machine learning, and optimization is something different, right? In the optimization, we still do all the simulations, while machine learning is sometimes these terms are being confused. Machine learning is something which is parallel to it. It can be used in it or not at all. Definitely, it's becomes more and more important when you have the data already. When you have a lot of data, then you can train machine learning algorithms on them. But as long as you don't have any data or any relevant data, then machine learning is useless. So don't confuse these two terms. We will dedicate some other webinars and some other effort to machine learning, but today we are talking about optimization, where we still simulate everything. Those are still simulations, but they are done in a loop in a smart way. most of the optimization loops means the shape optimization. So with the optimization, most of the projects, I would say the vast majority of projects means shape optimization. That means that we optimize the shape. So the object, the typical product, is changing its topology, it's changing its shape and size and its individual parts of the model. And shape optimization in terms of simulation optimization, it definitely needs something what we call geometry builder. That's important because geometry builder, it's a typical question. It's not part of our software, right? We know how to create one. We can recommend some external software like I don't know, CF Turbo cases and a few others that can help. That can work as the geometry builder. It means that from parameters, that's very important. We have parameters; those are numbers, I would say. And I would say with a set of rules, you allow this geometry builder to create the surface geometry. That's very important. So for shape optimization with CAE simulation, you definitely have to have the surface representation of the model. So it's 3D, but it's still surface. It's not a volume. I'm not talking here about the volume mesh yet, but it's the surface in 3D. That's very important. It's need to be created somehow, and that needs to be discussed a little bit in parallel, because every engineering office, every research department has different these pictures and these parameters, and it's impossible to create anything in general. But the geometry builder, if needed, but for most optimization loops, it's needed. It has to be discussed in parallel with the optimization project. A little disclaimer here: any optimization project brings quite a lot of new complexity into any problem. So optimization is complex, and it brings a new complexity to already complex field. So it's not if you begin with CFD simulations or FEA simulations, optimization should come on the stage sometime later, when you know already how to run your simulations. You are a little bit, I would say, confident about your results. Then the optimization makes sense, and then it makes sense to run it in full scale. It's relatively complex, and it needs some experience involved. Okay, so for optimization, it's in our software environment is responsible the opt module, which works in several modes. So it's a software module which, when used, it to standard workflow, which is typically meshing and CFD simulation, and that's pretty much it. It adds additional steps. It can create a simulation loop where a lot of simulations can be done, actually, and it allows the users to run simulations in several modes. So, for example, one of the typical modes is DOE. It's called design of experiment, and it can run the simulation in a way that we preset several variables, several parameters that they change, and with respect to rules we set, it's followed, and the opt runs a set of simulations, and we can then look at the results and decide what's the best result. Or the opt can be run in the optimization mode, which allows running it to it lives. I would call it. It lives its life. It iterates towards the best to best point in terms of the optimization function. So it can be even more interesting that you let it simulate and iterate towards the best possible in the preset parametric space. Yeah, so we have perhaps we will talk about it later in the presentation, but there are two optimization methods. The first one is called golden search algorithm. There are references for it, so it's relatively simple and quick. And the other simulation of the optimization method is called direct, and again, the theory is available, and it's an alternative. It's more complex, it takes more time, but it can take more, I would say, wild functions, optimization functions. Okay, so I will go ahead. So we did a couple of case studies of this such optimization workflow. The first one we would like to talk about it's by the way, it's also available on our website, and even all the details are available. That's important. So I will just mention what I find important on it. It's axial fan optimization. So we created a simple geometry builder in OpenVSP. So you can send the parameters there. Actually, the opt can do that, but you can do it manually. And OpenVSP brings you back the surface geometry. And based on these geometry builder, we have created a loop which allows us to run simulations like this. So this is the loop for this particular case study. So again, we start the simulation. The first initial mesh is created of the baseline simulation. Then the simulation is done, and then the opt decides what will be the next. Based on the rules we preset, it generates the new geometry. It creates the mesh, and again the new simulation is done, and based on the results. That's very important. That's why it's there, the simulation driven, right? Because based on the previous results, the next set of parameters is decided. The new, we call it parametric space point, the new point of parametric space is created, and then again and again, and it's a results driven, simulation driven optimization. It's being run. And yeah, as a result, here's a little animation. We have run something like 300, maybe 400 simulations with, I think, five parameters that have changed in certain bandwidth, and the simulation has run, and it iterated towards the best, I guess. I think it was the efficiency. The efficiency was the goal, and we did similar case study with centrifugal fan. So I'm not going to go to the details, but I'll just show a little animation how the simulation can be visualized at the end. So every little tiny white point is single simulation. So in the beginning, the optimization engine is quite kind of searching for in the exploring the parametric space, and then it starts the real optimization, and it starts iterating towards the best efficiency point, which is by the way in Turbomachinery, efficiency is very often the optimization function, the objective function, which is set, because efficiency is something we look for in most of the cases in Turbomachinery applications. Okay, so yeah, centrifugal fan, and similarly we did this for the blade propeller of drone. So again, it was, I guess this was well, Salome, I'm not sure. Maybe it was still OpenVSP again. The geometry builder created. Yeah, it was OpenVSP for sure. This is a mistake. It created the geometry, and again, yeah, pretty much the same story. It iterated towards the best efficiency. So it's this. Yeah. We have also one example. I don't know, maybe Radek will be talking about it or not. Anyway, it's not necessarily to run the optimization loop over the new geometries. You can be also looking for something else. For example, in this case, we created a workflow where we were looking for the maximum lift coefficient at the airfoil. So for this airfoil, for selected airfoil, what was changing was not the geometry, but it was the angle of attack. So we were looking for the angle of attack for which the lift coefficient is the highest, maximal. So it's as simple as this. So I guess this is the DOE still, and yes, and now it starts iterating around the design point candidates, and then it says, okay, it's some the winning design or the angle of attack. Okay, and before I will switch the presentation to Radek, I will finish this general part with an idea which resonates with me in the recent period, that the technology, here I mean the software and the workflow and the scripts and everything you use is just 40% of success. It's the smaller part of the success or of the quality of the results you produce in any CAE project. The rest is the knowledge and effort. So the knowledge is skills and experience. Your effort is your patience, your dedication. That's the bigger and the way more important part in any project, and in terms of quality of results and success. It's the way how you use it, with what effort and what knowledge. That's definitely more important than the technology. Technology is something which is great to have, but it's the smaller part of business. That's what I'm sure of. Okay, so I will definitely stop here and I will switch over the presentation to Radek. So let me see if he's still there.
Yeah, I'm still here.
That's great, Radek. Yeah, so the stage is yours. We can see your screen. Yes.
Perfect, thank you. So Luboš showed us several examples we did in the past, and all show some examples of possibilities what can be achieved with the TCAE, and particularly with the optimization tool. And now I would like to show you some practical example. So I took two examples. One is the simpler optimization that you do not have any geometry builder. So this will be just simple optimization of flow parameters or CFD parameters itself. So it doesn't require any external tool for geometry generation or any parametric model. So then we will show how to enable the optimization and how the optimization model TOpt looks like. And then on simple example, we will show how it looks or what should be managed or changed when we would like to do the geometry optimization. So we will not go for general or complex example like for this radial fans, pumps or whatever, because I think Luboš mentioned it, but I would like to repeat and emphasize that before you go for the optimization, you need to master the first step, so the mesh generation and CFD setup. So you have to be sure that your results are accurate, robust, and after this is satisfied, then you can go for the optimization, because it the optimization brings another level of complexity, and every mistake which is made in the first steps will be magnified within the optimization, and at the end you can get a crap and no trustable results after hours, days, or weeks of optimization running simulation. So first of all, we will show the example of the simple axial fan geometry in a segment, in the segment shape. So we just simulate the segment of the rotor and stator part of axial fan. And here we would like to, for example, find the best efficiency, not only the range of flow rate, but also for the range of RPMs. So this cannot be achieved, let's say, easily by DOE or by our guesses of the parameters, and to always to check for the efficiency. So let's look how to find the best efficiency point for two parameters, flow rate and RPM, so speed of the rotor. So at the beginning, you need to have the T-mesh and TCAE perfectly set up. So you need to several times run the simulation, check for the mesh parameters. When the mesh is okay, then you go for CFD simulation setup, which is the same like for all the other setup we presented in our previous webinars. So you set the standard parameters, and then you focus on the optimization. So mainly you need to focus on boundary conditions. So if you would like to go for combining the volumetric flow rate and RPMs, so you need to have at least these two parameters set following the optimization. So we have some based RPMs set in the standard CFD simulation, and then we have the volumetric boundary conditions. And so this we run, check if the results are trustable, if we got a nice and good results, and if this is okay, then we can go and we can enable the TOpt module. So simply you will enable the TOpt module. So the new item appear here, a new set of parameters. So as a contrary to what I said, that the optimization brings another level of complexity. So the setup of the optimization is pretty straightforward. There are just several parameters to be added, but this can make the workflow much more complex, and the first steps of the setup of the workflow has to be perfectly set and compatible with the future optimization run. So let's see what we can set. So for this case, in the general, in the TOpt menu, we have the operation mode. So as Luboš mentioned, we can run it in a simple DOE, domain of experiments, which means we explicitly say that some kind of combination of parameters will be run. So we explicitly say what RPMs and what flow rate will be set, and a fixed number of combination of parameters will be run. Or there is a optimize operation mode, which enables the optimization. So we just said, okay, the ranges of our parameters, and basically we can give the roof how many runs we need to run, or we would like to run to stop somewhere the optimization if some kind of criteria of convergence are not satisfied. Then the method, there are two options built-in method where you can choose the two algorithm implemented, golden section search and direct, as we can see in the presentation. And you can also use the external, which some kind of extended the possibilities of the workflow and the flexibility of workflow. So you can incorporate any external optimization tool. Typically, for example, the Dakota is mainly used, or it's one of the tool which is used for the optimization. So for some advanced optimization method or your in-house code, you can use the external method, and then by some scripting connection, you can enable to read the optimization parameters or to lead the optimization by the external tool. So let's stick with the built-in method. So now for the example, we will choose the golden section search. Because we will optimize, or for the optimization, the parameters will be chosen from the CFD parameters itself. So we do not need to add any initialization script. The initialization script typically is used to connect external software to generate the new geometry variation. So typically for geometry optimization, we need to implement the initialization script which connects the external tool, for example, the commercial one like CF Turbo or any other tool, to tell to the external tool which set of parameters, the geometry parameters, has to be now generated, and then the new geometry is generated and then put as the input for the meshing, for example, and for the simulation itself. Then there is convergent checking script, some kind of advanced tool. So if you need some advanced trigger point to check the convergence, so again you can implement a script or import an external tool to decide where the simulation should stop. Let's keep it without. We will not use it in this example. And now in the next menu, we have the optimization parameters. So here we define the parameters which we would like to vary, and based on these parameters, we would like to find a combination of these parameters to achieve, for example, the highest efficiency. Or another example could be that you have some, for example, Pelton turbine, and you would like to know the RPMs for a given head and the fixed torque. So then you can easily also define such a application. So you will vary RPMs, and the optimization function will be something like absolute value from the resulting torque minus your goal torque, and you would like to minimize this function, or similar function can be created. So here we have two parameters. So kind of the parameters is now keyword, which automatically shows you a list of all keywords which can be varied, which can be changed or which can be used as a parameter directly from TCFD or even for TMesh. So this can be also used some kind of for mesh convergence study. And the second parameter is again the keyword and is the volumetric flow rate. So is the boundary condition itself. The other parameters is how, for example, for DOE, what is the function of this parameter. So if it's just a linear space, or if the dependency is logarithmic, or even for some discrete parameters, you can put the list of values for the parameters. Then you define the minimum and maximum range of the allowed range of the for the parameter. Then for the golden section search, because golden section search needs to have some initial view on the parametric space. So you basically, by number of samples, you define the core for DOE simulation. So basically, if you have 3 samples for parameter 1 and 3 samples for parameter 2, then first 9 simulation with all the combination of these 2 parameters will be run, and then the golden section search starts from these results as an initial state. The group ID, if there are some connection between 2 parameters, that they share some dependency, then you can connect it to define some non-zero ID, and then these parameters can go together as a couple with the same dependency. So this can be also useful for some specific application. So, but now we have two parameters. So flow rate from 244 cubic meters per second and RPMs for 2000 RPM. Yeah, up to 5000 RPM. Then you can define your tracked quantity, so which quantity you would like to follow, and then will be visualized in the final report, and you will see all the dependency of these tracked quantity on the parametric space. So here we will follow efficiency, power, and axial force. For each of the tracked quantity, you can define the accept range. So the optimization can get rid of some unphysical values, because if the range of the parameters is too wide, it can happen that some parameters are out of the physical range of your machine. For example, at the given RPM, it cannot and cannot flow rate. It cannot generate any pressure drop or pressure rise in case of axial fan. So in case of negative or efficiency above 1, so all these results will be not taken into account to overall optimization results. And the same you can done for each quantity. All right, and finally, the optimization function you can define. So here the optimization function is simple the parameter of the efficiency which is evaluated, and we are looking for the maximum efficiency. Here you can define the relative or absolute tolerance. So if the next point, several next points differs less than these tolerances, then the optimization is stopped before the maximum runs are reached. So here for this example, because I run it tomorrow morning, so I just set maximum 20 runs, but it can typically go up to hundreds of runs for a single optimization loop. And then when you run it, you simply run the optimization by run all button, and then every step, every simulation is run, and during the optimization loop, you can follow every result you will have. So after any parametric point every parametric point in the space is evaluated, so then you can check the results, or even you can generate the report which will show you the current state of the optimization. So you can then read how many runs were run and all the results for each point in the parametric space. And for example, here the 4-point with the RPMs 2000 and the volumetric flow rate of 3 cubic meters, we have the efficiency more than 2. For example, the axial force is also negative, so it makes it some kind of shows us that these combination of parameters are out of the working range of the axial fan, and this basically this point is excluded from the optimization loop, and the same holds for the other points. The first 9 points, as we can see, was simulated with the DOE, and then from the 10 point, the optimization loop starts and it iterates towards hopefully the best efficiency point, because golden section search looks for the local maximum. So it depends again on the wildness of the optimization function, what do you would like to use. So with golden section search, you save time because it's simpler, but if the optimization function, or is expected that the optimization function has several local maximas, so then you need to go for the more advanced optimization algorithm. And at the end, you can follow your track quantities and optimization function for each simulation run, or then of course then you have a summary of the best efficiency point, so which point was the best one, and the combination of the parameters and resulting quantities the detect quantities. And then you can follow the graphs, the efficiency of each parameter with respect to the tracked or optimization function. And you can also see these 3D graphs, so the combination or the dependency of two parameters. If I enlarge it, so we have here angular velocity, here we have volumetric flow rate and the values of the optimization function. The green dots are the optimization results, the blue one are the results of DOE, and the red one is the best efficiency point. Yeah, and this way you can optimize what you want with a simple setup of the optimization module. Okay, so let's move for the more complex optimization. So here we have again the simple example of the geometry optimization. We have a simple pipe, banded pipe with 3 cross sections, and we can adjust the radiuses of these 3 cross section of the piping system. I will just show you, for example, this is the one of the best point, but if you can choose of another simulation point, we basically, there are 3 cross section, as I said, and we can manage the radiuses. And the optimization is set to find the best efficiency, which is just the lowest pressure drop for the flow in this pipe. So again, you start with a simple setup of the T-mesh and TCFD modules. So you typically load some initial geometry of the piping system. You set the mesh, you adjust the CFD parameters you would like to follow. I think in here we have the flow rate or inlet velocity, it doesn't matter. And then in the T-opt, we would like to connect some kind of external tool which generates us these variations of geometries based on these three parameters. So if I go on this just to show you how it looks. So if I go to the webinars, today's webinar, and here is the parametric pipe. So typically you have a folder with the external tool. So here it is a simple Python script which reads the 3 values of the radiuses, and this Python script creates us the STLs with the given shape. So this script reads the 3 parameters of the cross sections R1, R2, R3, and basically this generates the STL here into this folder. So it generates the inlet, outlet wall, and even for some kind of finite element method and optimization based on finite element method, it also generates some kind of solid for the piping system. But this is not a part of this example. So again, if you go to the T-opt module, so again, you can choose your operation mode, method, and algorithm. So here, as an example, we have a direct. Here you have the possibility to include the baseline run, which is typically you start optimization that you would like to optimize some existing geometry. So the existing geometry is the initial state, and the other results will be comparing with respect to the baseline run. So for example, you have some, for example, pump design, and you need to improve it. So you have this baseline geometry, and the geometry builder then will adjust the parameters by some relative values to optimize the current your baseline run. So therefore it's important to have the information about the CFD parameters of your initial state. So this is it. And the new, compared to the previous example, you need to create the initialization script which connects the optimization, basically which connects the parameters, optimization parameters with the external tool, and run the external tool to generate new set geometries to create a computational domain from the new set of geometries and run the CFD simulation. So here we have three parameters R1, R2, and R3. Now the kind is custom because these are the external parameters not connected to the CFD or TMesh module. Again, here you define simply the type for the dependency, baseline value to have the baseline design, and the minimum and maximum, so the range how the R3 parameter can vary, and again number of samples for DOE, and possibly you can somehow connect several parameters together. Okay, and this is all information we need to create a script. So basically what this script do is that at the end it run the subprocess is subroutine. This is Python script, so it runs the script or the external tool which generates the geometry, and it will add the current values of the parameters. Yeah, so what we need to do simply simply define or get from the TOpt or TCAE itself. So via this Python interface, there is a list of all the parameters which TCAE holds. So you have the access to any kind of parameters. So for example, TOpt number of parameters is the number which defines how many parameters you defined in a TCAE, basically, and particularly in the TOpt module. And then based on this number, you can get all the values for R1, R2, R3 parameters, and these values are then given to as a parameters to the script or to your external tool. And basically at the end, every loop, it runs the external tool with the current set of the parameters, generates the geometries, and the loop starts. So mesh is generated, CFD simulation is run, and the TOpt decides sorry, what will be the new set of the parameters, and again the scripts run the external tool, and again generates the new set of geometry, and the loop goes again up to the end of the optimization loop. So basically this part is the most complex one, to create the script and connect to the external tool. And typically with this part we help our customers to initially design the script to connect it, but when you get known about the principles, then it's pretty straightforward. And then again you define the tracked quantities like efficiency here, for example, or the total pressure difference. You set the accept range, you set the optimization function, and again run the loop, and as a result you will see the TOpt simulation report, where you see how many runs were run, and all the information about the parametric space, so about the baseline and all the other results depending on the combination of your parameters. And at the end you will see some kind of dependency like this, and again you can combine, of course you will find the best efficiency point, and then you can some kind of explore the parametric space and the influence of each parameter or on the optimization function. And then you can, based on the results, you can decide what will be the next step, or if you are done with the optimization. So these are the main principles, and basically all the other applications you can find on our web pages, like this centrifugal fan, axial fan optimization, like which Lubos already presented. So the principles are very the same. The connection is done with the external loop, external tool, and then you run the optimization in a loop. So we have run several such optimization in the past. Like for this centrifugal fan, we have this axial fan geometry variation and optimization. We also did some kind of optimization with CF Turbo, so to optimize the radial pump. So this was pretty extended optimization project with hundreds of loops, and really to explore the parametric space based on, I think, 5 or 6 parameters. We have some joint projects with the friendship system, and also together with friendship system and the Grid Pro, which proves how TCAE is flexible to be incorporated into any workflow, and really to combine several external tools for some really advanced application with some kind of higher added value for all the parts of the workflow. And the last one, yeah, we also did some kind of acoustics simulation for example for the DJI propeller, and on this we also do the optimization based on the geometry, but this can be also for future. We are planning to have some kind of optimization with connection to the acoustic parameters. All right, so I think I said what I wanted, so maybe now we can go back to Luboš, and maybe Luboš will add some additional information, or we can go directly for Q&A. And yeah, so Luboš, can you take over the presentation?
Absolutely, Radek. Thank you very much. Thank you for your contribution. It was again very informative and very interesting. Thank you. Yeah. So now I would like to ask the audience to ask your questions. I don't see many questions, so feel free to ask your questions. We will definitely like. It's our pleasure to answer them. For us, it's very interesting. What you would like to know. So feel free to ask your questions. And I will, before you do that, I will, or during you will be doing that. I will add a few comments. It's very simple, naive comments. I just realized during Radek's presentation. What definitely makes sense is by the way, I hope you can see my screen. It's not.
Yes, you can. Yeah.
I will do it in this mode. I can change it as I am presenting. So first of all, you should have to some level a reliable CFD. So I would not recommend to start directly with optimization without any experience with CFD. So you in ideal case you should have a reliable CFD model which you trust and which has some credibility, and then you can think about optimization. It's always in any project, it's extremely important to know what's your goals. What are your goals? What's your goal? What you need to use it for. It's extremely important. It's connected to the objective function, which has to be defined as early in the project stage as possible, because it's all about the goals. Without goal, you will never get anywhere. So goals are extremely important. Another important point regarding optimization is that with adding more and more parameters, the complexity grows exponentially. So low or less parameters is always better, because it's much simpler than more parameters. So it's just a little advice in the beginning. So number of parameters is extremely critical for any optimization. Then you have to deal with the geometry builder, because the vast majority of projects is aimed on shape optimization. So something is changing its topology, its shape. So the geometry builder has to come from somewhere. There are a lot of options. You can create one, you can get one, you can purchase one, you can get one done. It's really, there are a lot of options, and it's always individual. There are no general rules, because every engineering office or every research department has its customs, it has its spirit, and it's very difficult to make this general. Another point I have is, no matter how it looks in the webinar, it's the setting up the loop, the simulation loop, is simpler than it looks like. It's very simple basically, because when you have CFD, you put the geometry builder in, which is in the way of scripting. The workflow runs itself. The script on the background gets the new geometry typically and continues. So setting up the loop is not that difficult once you have all the steps, especially the geometry builder. The geometry builder is typical bottleneck. Geometry builder is typical bottleneck because it doesn't grow on trees. It's the more complex device, more complex product is, the more complex geometry builder is. So that's typical bottleneck. But again, the simulation loop creation is not a difficult process at all. And maybe finally, feel free to ask, because we did a lot of optimization projects in the past, and we are curious about the new ones, and we will definitely be happy to share our experience. So in Czech language, we say you do not need to discover America, right? In English, it's what they say, it's you do not reinvent the wheel, right? So we did likely a lot of things already. So feel free to ask, and we'll be happy to share our experience, and asking costs nothing. Yeah. So the Q&A is here. And actually, I have to say, I don't see many questions. I'll be honest with you. I haven't prepared my own questions. So, Vale, someone is asking how to install the software. Yeah, send us an email. We will share all the information. You can have the trial version. Those who are like students or something, we always make some deal. Don't worry about that. We are here for you. We'll always make a deal with anyone. So feel free to ask. We'll be happy to help. Okay, so we don't have many questions. So the typical question I remember from past webinars is the webinar will be is recorded, and the recording will be available. It's a typical question. And now I have run out of the question. So well, what do we do? Okay, I don't see many questions. I still see quite a lot of people here, but okay, the topic is very complex. So feel free to ask your questions anytime in the future. Yeah, cameras, maybe. Radek, let's show ourselves. If we don't have answers, let's show our honest faces. Hello. This is gonna be it. This is gonna be it. So thank you for your time. Thank you for coming to the webinar. We will definitely do our best in the future to help you. So feel free to ask your questions, and we'll be happy to answer via email or whatever. So Radek, what do you think?
Yeah. There is one last question.
Okay.
One and only question.
Yes, sure, please.
If we have any comparison study with ANSYS Turbo optimization done. So I don't know how this question is mentioned. So we do not have any particular comparison to another optimization, right? And we do not use the ANSYS Turbo optimization to be connected with TOPT or TCAE in general. Because to be honest, there are not much optimization comparison available on the web, right? To have all the information, because as you know, if you have any article which presents something, you are not able to get the data from which the article was made, right? So it's typical.
Sure.
So this is problematic, and we do not have any particular comparison.
Yeah. I have 2 points to this. It's possible. It's definitely our software is completely open-ended from all sides. It's extremely flexible, so it's definitely possible to connect it to any commercial code, even this one you mentioned. So it's definitely possible, and it would be a great competition with optimization tools, but it's relatively complex and it's relatively specific, very case specific. So it's very difficult to find any data or find any experience anywhere. But anyway, we're open to anything, so feel free to ask in the future. And I guess this is it, I think, right?
Mm-hmm. Oh, maybe a last question that appeared there. Which and how many optimization methods are implemented? Is the question by Pavel Kotalík.
Yes. Hello, Pavel. Okay. We have two methods, right? It's the golden search, which is a simple method, a very simple method, which it basically halves the intervals and in multiple dimensions and finds the local extremes, and then the direct algorithm, right? It's it was on one slide in the presentation.
And there is also the method external that you can also incorporate the Dakota tool, which consists of several algorithms, very advanced algorithms. So in this case, if you need any advanced tool, so then it can be used the external mode.
You're right.
So maybe next time we can do some webinar on this application.
We can do something with Dakota or with some external tool. I didn't mention it, and it's a mistake. Yeah, we should have mentioned this this feature. You can also use the external optimization tool easily. It's not it does not have to be the internal optimization algorithm. You can use you can use an external one which designs the parametric new points in the parametric space. Okay, but I think this is really gonna be it. So for all of us, I will thank you all for the attention. Feel free to get in touch, and we'll be happy to help. So we leave you with that, and bye bye for now.
Thank you. Bye bye. Thank you.